Okay, folks, so what we're going to do today is have a look at these two hypotheses, and that is whether or not the Earth is flat or whether or not the Earth is a sphere. And I'll try to take a serious look at this. Now, we've got alternative hypothesis that says that the Earth is flat, and if we look at the evidence and then we accept that, we therefore will be rejecting the hypothesis that the Earth is a sphere. Alternatively, if we find from the evidence that our conclusion that the Earth is a sphere, we will reject the alternative hypothesis and accept the null hypothesis. So let's start with the alternative hypothesis. So there's two possibilities. I'm looking at two models. Let's have a look over here. Okay, we've got two models going. Over here, the possibility that there's a flat Earth and above that an atmosphere. The problem is that this is not contained, and as a result, because our observations show that there's a gradient up here, we would have to contend with what happens on the sides over here, and how would the sun affect the atmosphere that's over there. So I would reject this one outright because it's nowhere near conforms to the observation, and it also spoils the notion from the flat Earth model that space even exists. That's number one. It would have to exist in this case, and also you would need a force to hold down the atmosphere. Okay, so let's cross that one off. That one is other than the flatness of it, is pretty much close to this hypothesis over here. So let's look at this one here, which is common and accepted throughout the flat Earth community. Now, there's quite a few people in the flat Earth community who purport not to have a model, which is equally absurd. So to say that you don't have a model, however, this one is not right, it doesn't work, even though it meets the observations, is nonsensical. Okay, so let's have a look at this. Here we have a dome surrounding. We don't know what that dome is. The flat Earth people will tell you that nobody knows what it is, and there's many different conjectures about what it might be. The idea that it might be some sort of crystal or some sort of glass, or I've even heard that it's some sort of liquid gas, and that came from a very, very tall gentleman in Thailand. Okay, so in this particular situation, just according to Dalton's law and gas laws in general, in this case, with the sun rotating and giving off energy, the surface of the sun is hot, so around 6,000, giving off energy all the time and going around here would cause the gas in this underneath this dome to become homogeneous. In fact, this gas would continue to heat up and become homogeneous. Right? Now, the other issue is has a fixed volume, so that would also increase the pressure underneath this dome. So there would have to be some mechanism for allowing that pressure to dissipate. Nothing of that is even proposed. Okay. So the fact that this would have a fixed dome has problems associated like this. Okay, let's have a look at what the evidence would be expected from this. Okay, so if this was a fixed dome, first of all, this is what you'd expect, increasingly hot gas and temperatures as a function of time. So the longer that time went on, and remember, if we believe the creation story, there's 6,000 years in here, So at 6,000 years, this sun has managed to go around here underneath this dome, and that would have, in that time, caused a massive increase in temperature. We can actually do the maths on that and work out exactly how many calories of energy would have dissipated by then, and how much this gas would have raised. But suffice to say, it would be a significant temperature increase for all the gas under this. Okay, there would be no pressure gradient in here. Okay, all the gas would be homogeneous. If there's any convection currents, there would be convection that you normally expect, where things heat up, rise, come back, just like you'd see convection currents that happen in a pot of water, for instance, on the stove. So that would be a rotating convection current around there, but pretty much the gas molecules would be homogeneous, and certainly be roughly the same temperature. Okay, the fixed volume is a real problem here, okay, because it's going to have an increased pressure. So as the temperature increases, the pressure will increase as well. We know that from Boyle's equation. And so if we fix the volume, temperature and pressure are proportional to each other. Now, so again, this has had enough time. 6,000 years with the sun above there creating this additional temperature in a fixed volume would have created a significant amount of pressure. And certainly there would be no gradient pressure. This pressure would be homogeneous through the entire system. Okay, so again, increase in temperature with altitude. So again, you'd expect, if indeed we did have this convection currents running through here, which I think we would, then we would have an increase in temperature as you went up, because the closer you got to this source of energy, the sun, the hotter things would get for you. Okay, that would be undeniable. Okay, altimeters would not work. So because of this homogeneous pressure in there, then altimeters are basically barometers and work off pressure. And because they don't have that, this would be homogeneous. Therefore, the altimeters wouldn't work. Okay, so the conclusion here is this does not comport with actual observations. So these evidences that are expected do not comport with the actual observations. Okay. All right, let's look at the other one and then and see what we can get from that. So over here we have the globe model, which is the null hypothesis. Okay, in this particular model, there is a pressure gradient close to the surface, as you can see depicted here. The gas is much thicker, more molecules, if you like, per cubic meter as you are closer to the Earth, and then as you move away, it gets less and less, and you see depicted up here practically very, very few molecules compared to what they are down here, and compared to the size of the space that's been occupied. Okay, so if we have a look at that, we can see here a great pressure gradient, high concentration of molecules close to the surface, low concentration of molecules. So I'll write that up. So low concentration of molecules much further away. And this arrangement just keeps going indefinitely. So because of that, there is no requirement for a barrier between the two. So what the molecules that are close to the surface are being held there by gravity, and one would say, well, do we get some of the atmosphere leaking off? Yes, that does happen. Okay, but by and large, the energy that's required to make it leak off is less than the force that gravity is acting on it to keep it to the Earth. And so some people will say, well, gravity is not a force. When gravity is applied to a mass, and gas has a mass, drop a kilogram of carbon dioxide on your foot, and then come back and tell me that it doesn't have mass, I'm afraid you'll find that it does. So gases do have mass. Force will act, gravity will act in concert with mass to create this force, and it's this force that keeps the molecules on the planet. So, basically describing that in this equation, that force is equal to the mass times the gravitational acceleration. Okay, now, what evidence would we expect to see because of this? We would expect to see that as you get up higher and higher in altitude, you'd have less and less gas, so you'd find it a struggle to breathe if you were, say, at the top of a mountain. Now, does that comport with the observation? It certainly does. If you climb a high mountain like Everest, you'll definitely have to take breathing apparatus with you. Okay, people die up there because they don't have sufficient air to breathe. Okay, so pressure decrease with altitude. So as you go higher and higher in altitude, the pressure gets less and less, and this is expected because the molecules get less and less. So there's fewer and fewer molecules bashing into each other, fewer and fewer molecules creating mass. The pressure will definitely increase as you go up, and it does. This is a measured fact. Okay, the pressure decreases as you rise. Okay, so as you go from the bottom of the mountain to the top of the mountain, not only does it make it impossible to breathe because there's not enough gas, but the pressure also decreases. We know the pressure decreases too because if you wanted to boil water, for instance, at the surface of the Earth, you'd have to boil water. It would be boiling at around about 100 degrees C, 200 and 373 degrees Kelvin, and then as you go up towards the top of Mount Everest, that it would boil at 70 degrees C. Okay, so that's considerably less. So because it's boiling at much less temperature, that proves that the pressure is much less. Okay, temperature will decrease with altitude. That comports with observations as well, and it's a fact because there are less molecules up there. There are less molecules to heat up, less molecules expressing the energy that's up there. So for that reason, the temperature decreases. So temperature relies on the fact that there are things to heat up, such as some sort of mass to heat up, and because there isn't enough of them around, therefore there isn't enough energy, and therefore it gets colder and colder the higher up you go. People will say, well, what happens in the thermosphere? Okay, well, again, the amount of temperature, there isn't a blanket amount of temperature around. You can't say, well, I'll go from here to there and then all of a sudden it's going to be hot. It's nothing like that. Hot relates to particular items that are in that vicinity. Okay, everything else around it is cold, and I mean really cold. So approaching absolute zero. So we talk approaching 0 K, right, which is minus 273 C. So things that are approaching that temperature, absolute zero, in areas where there is no energy or very little energy. So when items are there and they're exposed to the high energy, then they become hot, sure. Okay, what else have we got here? We got low concentration of gases, okay, at high altitude. So I think we've gone over that. So again, this low concentration at high altitude, well, aeroplanes can't fly beyond a certain altitude because there just isn't enough air for them to be able to fly through. Aeroplanes need to be able to have an amount of air that passes over the top of the wing and a number of air that passes below the wing, creating this pressure difference which gives the airplane lift. So it's got two issues, the airplane, with that. Number one, it doesn't carry around sufficient of its own oxygen like a rocket does to be able to not need oxygen from the air that's around it. So if it's too high, there's not enough of it to sustain combustion, and again, if it's too high, there's not enough of it to maintain lift, so the aerofoils don't work. Okay, now in a nutshell, again, this is quite brief. We could probably take both models to much greater extremes, but this is going to be a short video. So again, all of these evidences comport with the observation, all of them. Okay, so now let's draw some conclusions from the evidence that we have on this board here. So based on that, does not comport with observations, that these evidences that would have to be available if this model was right. These things here, no gradient, for instance. Okay, if we had this dome, all of those things would have to be true, and that does not comport with actual observations. Over here, in this case, all of the evidence, all of those that we've been through there, comport with actual observations. So we can only reach one conclusion. In this case, we have to reject H1, the alternative hypothesis, and we will accept the null hypothesis. The Earth is in fact a sphere. Thank you.